This lesson is going to be about relative motion. So relative motion is how an observer views an object in motion within a medium in motion. So in other words, you might perceive motion to be one thing, but in fact, it might actually be another thing. So for instance, I've got two little quick videos here. I hope they turn out, a video recording a video, if you will. So this was just pulled off YouTube. A skier had a GoPro on, or maybe they just use their phone. I don't know the actual context here, but from the skier's perspective, they are at rest, and it looks like the snow is moving past them, which in reality, we know the skier is probably just going downhill. But from his frame of reference or her frame of reference, they are at rest, and it's the snow that is moving. So that's mainly because all motion is relative. So another little video I have, which is more of an animation. You guys have lived through winter once or twice. I assume you've driven through winter once or twice. So the snow was falling down, straight down, when the driver was not moving their car. But as you can see now, if we were the person driving the car, it looks like the snow is going towards the screen. Change and look to your left. Now it looks like the snow is moving to your left. Look behind you. It looks like the snow is moving away from you. And then again, look to your right, it looks like the snow is moving to your right. So all the motion is relative to your actual current velocity. So that's something that's kind of hard to portray. For instance, there's no real at-rest position on Earth, because technically Earth is always rotating on its own axis. It's always rotating around the sun. And of course, our solar system is rotating amongst the black holes at the center of our galaxy. So basically, there is no absolute at rest. All you can do is really compare one object's motion to another object's motion. So that's kind of what we're going to look at today, which means we're basically going to be doing something known as Galilean velocity addition. So in other words, you basically add two velocities together. So if I look at this little stick figure in the middle, this little stick figure might perceive this car traveling at 25 meters per second to the right, and would perceive this car traveling 35 meters per second to the left. Whereas if I put somebody in this car, according to them, would be at an absolute rest. And if this car is technically traveling, the person inside this car would say that this man, or the stick figure, is moving left at 25 meters per second, because once again, if you're inside this car, they are considered to be in an at-rest state. Anytime you are driving in your vehicle, you are just sitting there, you are at rest. You can look outside your window and you'll see trees move past you if you're driving your vehicle. So to your perspective, to your relative frame of position, you are at rest and the trees are in motion. If I look at this car here, this car again, the red car, is at rest. Probably can't see my mouse. There we go. This red car is at rest, and therefore we perceive this lime, I don't know what color this is, lime car traveling. So again, if this guy's at rest, you would actually add these two velocities together, the 25 meters per second and the 35 meters per second. Right? So you would see both of those added simultaneously, and the person in the red car would say that this lime car is traveling 60 meters per second towards the left. So relative motion just typically involves a lot of adding of velocities. So if you've ever had to dock a boat at your lake or whatnot, or if you've ever been in a boat in a river, you know you might be pointed one direction, right? So if you look at this little rowboat guy here, this little rowboat person is going towards the right. That's the direction they're steering, but the current itself of the water might be pushing that rowboater down on the page. And so therefore the overall relative velocity of this boat is going to be going and observing both of those speeds at the same time, because the boat has a certain speed and the current has a certain speed. They both have different directions, and so we end up with some velocity addition. Likewise with airplanes, whenever we view our airplanes, they might be pointed in one direction, the wind might be pushing them in a different direction. And of course, what you would see on the ground is their overall velocity. All right, so that's maybe not something you would notice if you're in the plane, because when you're in the plane, you just see the clouds go by and you look down and it looks neat. Everyone looks like a bunch of ants. Way back in about 2006, I want to say, there was a really windy day in Calgary and all of southern Alberta. And a friend of mine took this video near the Calgary airport. I'm going to mute the sound because I think you get the idea. It's windy, so you just hear the wind. When you look at the plane now, you don't really notice too much. The plane is just getting ready for a landing. All right, so just let this play a little bit longer. It's a very, very windy day, I must add. And so when we get right about there, oops, put the plane in the picture a little bit more. So right about there, I'll pause it and you can see what direction the plane is actually headed. So the plane is going more to the left, but the runway is sort of straight and a little bit to the right. So the wind is actually pushing the plane to be going along the runway, but the plane is not headed towards the runway. The plane is pointed somewhere else. So what we're witnessing is relative motion in action. So of course the plane landed, the pilot was pretty good. All right, plane landed just fine. Everyone landed safely in Calgary. We're happy, good to go. Air Lithuania, I believe, is what that plane is. So if we actually look at a little still that I took of that picture earlier, all right, so this is a three-dimensional grid. So if I create a X, Y, Z axis to indicate what the plane's actually doing, the plane is, this is my attempt to draw in 3 dimensions. So the plane looks like it's headed towards that orange vector arrow, but what we see on the ground is the plane traveling down this magenta arrow. So if I look at it from the top view is probably a little bit easier to digest. So there's 3 velocities in play here. You've got the plane speed with respect to the air. So it has a certain direction. So we can call this the plane velocity with respect to the air. So that would be this right here, plane velocity with respect to the air. That's the direction the plane's actually traveling. It looks like it's trying to go in this direction here. The wind is blowing pretty hard, and so that would be the velocity of the air speed with respect to the ground. And so that is adding on to the plane's velocity and pushes it and changes its direction and changes its overall airspeed. So what an observer from the ground, observer at rest on the ground, that's what we're going to work on here in Physics 30, is assuming that somebody is watching standing still on the ground. So that person is going to be called an observer on the ground. So that's where we're going to take it as an absolute rest. Obviously, they're in motion if you consider the Earth, but moving as well, but we are not going to get that detail. So this is what we saw watching the plane. We saw the plane's actual ground velocity, the velocity addition or the relative motion of 2 separate velocities all traveling in medium. You don't see this as much in your car because you're stuck on the ground and road friction tends to beat any kind of wind velocities or air velocities to change your overall direction. And so therefore you see this more with boats, you see this more with planes. So here's another little animation, kind of give you a rough idea. You might notice the tailwind and headwind more with your cars when you're actually driving to and from whatever neighboring towns. If the wind is at your back, you'll have less, you'll burn less gas. In other words, your car will have an easier time with it. If it's a plane, it might actually cause the plane to go faster. If you have a headwind, it's going to be going against you. So that's this guy right here. It's going to cause the plane to go slower, but if this is your automobile, you would just burn more gas because now you're going against the wind as well as road friction. If you got a crosswind and you're in the plane, you would be adding both of these velocities together. And so this is a little bit that I kind of just drew on there. So you're getting both velocities acting on the body simultaneously. And so even though the plane is headed down this blue path right here, this blue vector arrow, what actually happens, the wind gets added onto it. And so of course it changes the overall velocity. And what we see is the green path, the relative velocity of that plane with respect to the ground. Mythbusters did this. They took them off quite a bit of trial and error. So this is just a quick little 2-second clip of probably an hour-long episode. So what Mythbusters did is they took that in consideration, relative motions. They thought, well, what if we fired a cannonball? It's actually a soccer ball. What if we fired a soccer ball in the exact opposite direction of the truck in motion? So I believe the truck was moving 60 miles per hour to the left on the screen, and they fired a little cannonball 60 miles per hour to the right. And so with velocity addition, 60 to the left plus 60 to the right should give you 0. There's a lot of trial and error because firing cannons doesn't always give you the exact correct velocity that you plan on because physics is hard. But after quite a few trial and errors, they actually were able to show it. So relative motion, us, the camera people, and people watching on the screen, we just see a ball fall straight down. All right, and so that's kind of an idea of relative motion. We know it was fired to the right, but of course the vehicle was in motion to the left, and so the two velocities just cancel each other out. So this is another example of relative motion. The people in this train, or I think it's a train, are at rest. To their perspective, the camera looking outside the train shows the tree is in motion, the cars are in motion, the houses are in motion, everything else is in motion. So everything is in motion relative to these observers at rest. Now we know houses and trees don't move, but again, that's the idea behind relative motion. You have to put yourself in a different frame of reference. Okay, that was too much talking. Let's actually do some math. I've got some of this pre-drawn just to keep our life a little bit easier and make this video a bit shorter. So two questions I'm going to go through. One's a plane question, one's a boat question. So this plane is traveling northeast through the air with an airspeed of 250 kilometers per hour. The wind is blowing 50 kilometers an hour, 30 degrees south of west. What is the velocity of the plane from an observer's point of view on the ground? So the observer will see both the plane and the wind acting simultaneously. So we're going to follow this basic equation. So the velocity of the plane with respect to an observer on the ground should be equal to the velocity of the plane in the air. So with respect to the air velocity plus the velocity of the air with respect to the ground. So in other words, the wind. This one guy is going to be the wind velocity, and this guy is going to be what the pilot is actually planning on doing. What we're going to try to find is the resultant vector. So to do this, I do have it pre-drawn out. I have my scale set for every 1 centimeter is 50 kilometers per hour. And so again, I use the correct drawing tools. If I connect them all together, which you don't have to, you can draw them separately. In a case like this where you have a very small wind velocity, I would maybe draw them separately, like I kind of have now, but I'm going to just still connect them together anyways. So this black vector arrow, that would be the velocity of the plane with respect to the air. And so we know that to be 200, I'll scroll up, 250 kilometers per hour. So I'm going to write it down, 250 kilometers per hour. So we know that the direction is a 45-degree angle. I know it's a 45-degree angle because it says it's traveling northeast. Since there's no number written down, that means it splits the north axis and east axis evenly. And the only angle that could be would be 45 degrees. So the information they gave us in the question says that this is 45 degrees, which also means this is 45 degrees. So what I'm going to do is I'm going to do some vector addition. And when you do vector addition, when one vector stops, you draw in your new vector. So at the very end of this vector, so I drew it to be 5 centimeters long because with my scale, 1 centimeter is equal to 50 kilometers per hour. I'm going to drag, oh, that's not good. Technical difficulties while recording. I'll drag this over here and I will connect this vector at the actual head of the first vector. So that would be the green vector arrow there. That would be the velocity. I'll write it in green. So that is the velocity of the air with respect to the ground. And that is, of course, 50 kilometers per hour. So it's only 1 centimeter long, and it is at an angle. So in the question, it says it is going 30 degrees south of west. So the way that's written means it is west 30 degrees towards the south. That's usually the way I prefer to write them down anyhow. So as you can see, it's going a little bit against the actual plane. And so if I want to draw in the resultant plane velocity in the end, I just need to basically connect the two dots. So again, I did pre-draw it just so I can grab it over here. I would just connect the two dots with my ruler and pencil. I would start at the very beginning here, down below at the black, and I would connect my little magenta arrow to the tip of that green. So that would be the resultant velocity of the plane velocity with respect to the ground. So velocity PG is what we're looking for. Next order of business, I would like to break this down into x's and y's. So I'm going to consider that x vector, I'm going to consider that y vector. And so therefore, since it's a 45-degree angle, I know that my x value, I'll call this x1, I'll call this y1, when it's 45 degrees. So at a 45-degree angle, your x value is going to be equal to your y value in magnitude. So that's kind of a nice little thing to remember, cuts down on some of the work. So that means I'm just going to solve for my x and make my life a little bit simpler. So in this case, I'm going to want to take the velocity of the plane with respect to the air. I'm going to multiply it by cos of 45. And so that means I'm going to take 250 kilometers per hour multiplied by cos of 45. And I should get 176.77 something or other kilometers per hour. So as a friendly reminder, when I do a lot of my trig, I don't round my answers in my calculator. So whatever I write down on the screen here, there's more digits that come after it. I might round up or I might round down, but when I look at my calculator, my numbers in the calculator are going to be whatever they're going to be. So since I found my x and I know it's a 45-degree angle, I can just take a quick shortcut and say that the y velocity is also 176.8 kilometers per hour. So you can only do that when you have a nice 45-degree angle. One equation to rule them all. So my velocity of my air, so my wind velocity, if you will. Now this is a much smaller triangle, so I'm not going to really be able to put much in there, but I do know that the small little angle right there is 30 degrees. So I'll just do that off to the side and I'll color coordinates. I'll use my green. So this will be, I'm going to call that x2. X2 is going to be the velocity of the air with respect to the ground. So in other words, it's the wind velocity. And that's going to multiply by its angle. So I'm going to measure from the x-axis. So therefore, I'm going to use the 30 degrees that is provided for me. So plugging that in, I know that I have 50 kilometers per hour multiplied by cos 30 degrees. And so my x velocity of the wind should be approximately 43.3 kilometers per hour. And again, that has some rounding going on. And then if I want to find my y value, so this would be my y value right there. So it's a very, very small triangle again. So you can draw this off to the side somewhere else, right? Don't be afraid to make a separate scale. I'll just do that real quick. This is not to scale, obviously, right? Don't be afraid to just draw a separate scale if you want. Right, so that's my 30 degrees. That's the velocity of my wind with respect to the ground. So I just found that value there. I'm going to look for my y value here. All right, so if you need to do a separate scale off to the side so it's a bit more visible for you to actually understand what you're doing. Okay, so y2, same idea. Velocity of the air with respect to the ground multiplied by sine 30 degrees. So that's my same 50 kilometers per hour times sine 30 degrees. And that should give me a 25 kilometer per hour velocity in the y. So next, I've got to do velocity addition. So with velocity addition, I'm going to take the velocity of the plane with respect to the air. That's the pilot actually driving, flying the plane, plus the velocity of the air with respect to the ground. In its component forms, and find the velocity of the plane with respect to the ground. So to do that, I'll have to plug in my numbers. So the velocity of the plane with respect to the air was 176.7 kilometers per hour in the x direction. The y direction was the same value because it was a, 0.8, rounding, kilometers per hour. In the y direction, it's going north and east, so both of them are positive. Now the wind is going west and south, so the two numbers I just finished calculating should be negative values. So west would be negative 43.3 kilometers per hour. In the x direction, I'm going to add to that a negative 25.0 kilometers per hour in the j component vector. So add all those together, you will get 133.5 approximately kilometers per hour. So it'll be a positive value there, and we're going to add on to it another positive value of 151.8 kilometers per hour in the j. So in both cases, it's a little bit slower than the actual, what the pilot's actually doing, but that seems pretty obvious when you look at the resultant vector there. Right, that resultant vector is a little bit shorter. So what we just calculated is the y velocity and the x velocity. So that's what we just figured out. So I do have that pre-drawn already. So this would be 151.8 kilometers per hour, and this guy up here is going to be 133.5 kilometers per hour. My radian is worse than normal today for some reason. So those are my x, that's my y. The last little bit here is to find Pythagorean theorem. So we're going to have to find the hypotenuse and to define the angle. So the velocity of the hypotenuse, if you will, the velocity of the plane with respect to the ground squared should be equal to its final x squared plus its final y squared. Okay, so we'll just plug those two values in to that, and you end up with 133.5 approximately kilometers per hour quantity squared plus 151.8 kilometers per hour squared. And then add those together, take the square root. I'm not going to show that step. And you should get approximately 202. And I'm going to default that down to 3 significant figures. So that is the magnitude of that magenta resultant vector. So if you drew it off the scale, you'd probably find it to be 4 centimeters long. If you followed the scale for every 1 centimeter is 50 kilometers per hour. Now, the last thing I'm going to do, I typically like to measure my angles. I usually like to measure my angles for my x-axis. So that's usually where I like to measure my angles. So I can take that same 133 along my x, 0.5 kilometers per hour. That'll be my adjacent side, and this will be my opposite side. So I'm going to still use these two numbers. It's just I'm going to use 133 as my adjacent side and 151.8 as my opposite side. And that diagram is starting to look quite messy. So to find my angle, I'm going to take the inverse tan function of my opposite. So this is my y divided by my adjacent. So therefore, I'm going to take that as tan inverse 1 of 151.8 kilometers per hour, all divided by 133.5 kilometers per hour. Do the inverse tan function of that, and you're going to get an approximate angle of 49 degrees. So when I write out my final resultant vector, the velocity of the plane with respect to the ground should be 202 kilometers per hour. I would write it down as east 49 degrees to the north. I write east first because I'm measuring from my x-axis. I know I'm measuring from my x-axis because I put my x value in my denominator. So I have x there and I've got y there. And so when I put my x in the denominator, I'm going to want to make sure that my first letter here, when I write it down with this navigator method, should be first. So that is kind of what you would be expected to do. Sometimes I get mean on tests and quizzes, and instead of making you solve for the velocity with respect to the ground, I might make you solve for this guy or this guy, and at that point you have to do some vector subtraction. But as you know, that's not a big deal. Okay, this part I had to re-record it because the audio cut out, so let's just continue this on. Boat is traveling across a river that flows due east at 8.5 meters per second. The boat is aimed 15 degrees upstream and can travel 11.2 meters per second at top speed. How fast and in which way is the boat moving relative to the banks of the river? So river problems are very much like airspeed problems and velocity plane problems, in that you have an object, a vessel, if you will, moving in a medium. So an observer on the ground is going to witness both the vessel, so the boat in this case, and the medium, the water in this case, moving simultaneously. And so that is their end goal. What does someone on the ground perceive this to be? So if we follow this basic equation here, so it's kind of the same equation as the velocity of the plane question, where we have relative to the ground is equal to relative within the medium plus the medium moving itself. That's kind of what these symbols mean. We should be able to figure this out. So I typically draw a river in most of my river problems just so I can kind of visualize what's happening here. So I just draw typically two horizontal lines, and that's usually good enough for a river. So if I want to draw this boat to scale, I'd probably take my ruler and draw a 11.2 centimeter line at a 15-degree angle. So my measuring utensils are up here. I won't bore you with how to actually draw an angle at 15 degrees. So I would say it's going upstream. So it says 15 degrees upstream in the question. So to me, that means it's going to the west if the river is flowing due east. So that's why I aimed it up 15 degrees to the left here. I didn't say if it was going north or south, so I could have drawn this thing, if I just get my pencil in here, I could have drawn this thing at 15 degrees going south if I really wanted to. I just chose north for no reason. In the end of the day, it's not going to matter, and I'll show you how I represent my answer in this context. So if you just draw it, assume it's going north for now, that should be good enough for our purposes. So we drew in the I drew in the velocity of the boat with respect to the water. So the boat is aimed going to the left and up as it flows down the river, or up the river. The river itself, so the velocity of the water with respect to the ground, is going to the right because that is due east, and it would be about 8.5 centimeters long. If I do the scale, 1 centimeter is equal to 1 meter per second. And so that one should be a nice easy line. It's actually a one-dimension vector, so that keeps our math actually a lot easier than the previous question. So knowing that I'm going to have to add these two vectors together, I'm going to break them down into their x component and y component. So I broke it down into a right angle triangle. So to find the velocity of the boat with respect to the water in the x direction, I would just take the equation, kind of got ahead of myself here. I would take the equation, the adjacent side is equal to the hypotenuse multiplied by cos of the angle, and so this case is going to be 15. So I just take my 11.2 meters per second multiplied by cos 15 degrees, and I should get 10.82 meters per second. So if you drew this to scale, this line would be about 10.8 centimeters. Odds are good you won't be able to get that extra 0.2 in. And then you do your vertical section. So the vertical section, same idea. This is my opposite side of my 15-degree angle. So the velocity of my boat with respect to the water in the vertical, so in the y direction, should be equal to the hypotenuse times sine of 15 degrees. And that should give me about 2.9 meters per second, which you should be able to measure that as 2.9 centimeters. So that's my x and my y components. So I would get it set up like this. I'd write it down in this rectangular format where you have these component vectors. So I'd write it as negative 10.82 because it's going left, it's going upstream, so that would be west. So therefore, don't forget to make this guy negative. And because I decided to make this going north, not that the question told me to, I just felt like dealing with a positive answer or value. So that's just positive 2.9 meters per second in the vertical. to input in my velocity of the water with respect to the ground, I would just plug it in as an x value plus a 0 on the y, because there is only an east direction. So that one, like I said, is just one dimension vector, so that one's not too bad to do. You're just going to add these two together. So you'd add both the x's together, you add both the y's together, and your outcome should just be negative 10.82 plus a positive 8.5. You'll get negative negative 2.32 meters per second in the x direction. So that's the I component vector, and then 2.9 plus 0 is 2.9. So there's no real thought process behind there. So you've got your x, you've got your y value, and the way you draw your resultant vector, you begin at the very starting point, or you could just draw it off to the side. It doesn't matter. You can draw it off to the side somewhere else, right? Your 2.3 in the left, and then your 2.9 going up if you really want. I connected my vectors together, and so it looked like this, connecting from the beginning, touching the ending point here. You write down your x and y component values if you'd like. It does get a little bit convoluted and messy if you draw all vectors in the same diagram. Sometimes I just draw them off to the side and keep all my vector components separate. But how you do it is up to you. So from there, we know our x value, we know our y value, and we're looking for our angle theta, and we're looking for our hypotenuse. So it's just a matter of doing your Pythagorean theorems, the velocity of the boat with respect to the ground, because this is the path that we are going to see. Even though the boat is aimed going up and left this way, we're going to see it be a bit more steeper because the river's going to change its actual overall direction. So Pythagorean theorem tells us that if we take 2.32 meters per second squared, add it to 2.9 meters per second squared, then take the square root when you're all said and done, should give you a value of approximately 3.71 meters per second. So again, if you got your ruler involved, this would be about 3.7 centimeters. We also need to find the angle. So my angle theta there would just be taken by, you find it by taking the inverse tan function of my opposite side. So in this case, this is my y from this angle, divided by the adjacent, which would be the x. So in other words, you'd have your 2.9 meters per second divided by your 2.32 meters per second, and you'll get approximately 51 degrees. So then to write it in the proper format in the end, you write it down as the hypotenuse, 3.71 meters per second, at an angle 51 degrees upstream. Now I say upstream because it wasn't specific as to whether or not the boat was going north or south. Often you would probably, especially if this was an exam, you'd probably be told if it was going north or south. I don't usually like to leave things up for you to make a decision math-wise. That sounds kind of weird. So if that was the case and we were going north, you would probably write it down as east 51 degrees to the north. If you were going south, it'd be east 51 degrees to the south. But since it wasn't specific as to whether or not the boat was going upstream, going north or south, we just kind of leave it as 51 degrees upstream and just call it a day at that. So I hope that was helpful. And if you have any questions, just fire me an email. Some of these questions do get a little bit difficult. For instance, sometimes you might have to solve for the velocity of the water with respect to the ground. And just like I said in the previous example, you would have to then do vector subtraction because you'd bring this guy to the other side. But that isn't too horrible. So try questions on page 20. They vary in difficulty. And yeah, if you have any questions, fire me an email and I'll get back to you as quickly as I can.